This is Jeffy. Say hi, Jeffy.
Hi, Jeffy.
He has a lot of issues. First off, a lot of colleges want their money back. Iowa and Georgia Tech have been chasing after him to pay back his student loans.
Unfortunately, his job doesn't pay all that much.
His brother tried to help him, but he said,
No!
After considering all the possible outcomes, he decided to fake his death.
he didn't know exactly how he would do this.
And that's where we come in.
We took Jeffy's request and decided to send him into an actual tornado.
A couple of issues came up when calculating this complicated brain twister.
First, we had to get an idea of what we were dealing with. So, we binge watched several shows and movies such as Storm Chasers, Twister, and Sharknado in order to have the best sources for our project.
First, we decided to see if these two velocity fields were rotational or irrotational.
We were given two tornadoes represented by vector fields. In order to find out if they are rotational or irrotational, we had to calculate the vorticity, which is the cross product between the gradient and the velocity field. If the vorticity is equal to 0, which it is, we have a tornado that is irrotational.
So for part B, we were taking the two velocity fields that we had in part A, only this time we had an additional stream function given u equals psi y and v equals negative psi sub x. And what we had to do is we had to show that the gradient of psi of cross product with the gradient is equal to negative zeta. And we were eventually able to show that negative zeta is equal to 0. So what we do is we took the gradient dot product with the gradient of psi, and once we found out the dot product of that, we found out that it was equal to 0. We eventually started computing the k component of that vorticity, and we found out that it eventually was equal to a 0 vector. And then once we found out, we set that equal to negative zeta, and we got 0 for both answers. Moving on to part C, we're given a stream function psi, which is equal to sine x sine y over a square region R. And what we had to do for this part C, we had to find the components u and v of a certain velocity field. And we got that they were equal to sine x cosine y and negative sine y cosine x. And then what we had to do is we had to sketch this on Mathematica over the square region, which was given to us as x between 0 and pi and y between 0 and pi. So let's go ahead and take a look at Mathematica.
As you can see, this vector field looks like a tornado. Hi, it's Jeffy. I'm back. And because I didn't want to die, I told the boys to figure out where I should stand relative to the tornado.
So we decided to find the maximums and minimums over the region R, or for starters, the safe and unsafe spots.
Let's move on to our work.
Okay, so for part D, we want to find the vorticity function for the stream function in part C. We're going to do it over a region, x from 0 to pi and y from 0 to pi. What we're going to try to do is figure out where all the maximums and the minimums are for the vorticity function. This will let us know where a person should stand and be most likely to survive and where a person should not stand. So as you can see here, we calculated the vorticity function, and then next what we did was found the partial derivative of the vorticity function with respect to x and with respect to y. What we want to do then is set both of those equal to 0 and find the critical points. The critical points will be where, like I said, both of these are equal to 0 and they're also equal to each other. As you can see here, we found several critical points. All the points from here over are all boundary points, whereas pi over 2 and pi over 2 is not a boundary point. Next, we calculated a, b, and c for the vorticity function, as you can see here. And then using ac minus b squared, trying pi over 2 and pi over 2, we get that ac minus b squared is equal to 4, which is greater than 0. And also, calculating A, we saw that it was less than 0. This tells us that pi over 2 and pi over 2 is a local maximum. Trying all of these values and also anywhere else on the boundary here gave us that the vorticity was equal to 0. So that tells us that anywhere on the boundary there is a minimum, and at pi over 2 and pi over 2, which is the center, we have a maximum. So if you were going to go into a tornado and you wanted to know the least likely place to die, you'd want to stand anywhere on the boundary, and the most dangerous place is in the center because that's where the maximum is.
As you can see here, we used Mathematica to plot several of the level curves for the vorticity function that we found in part D. According to our calculations, it will be safest for Jeffy to stand on the outer edge of the tornado. But sadly, Jeffy does not listen to his students.
Amen.